go through actually doing a fit to an intrinsically linear model in Excel. And so what I have here is a set of data x and y. You can see it kind of looks linear, but it's actually growing a little bit faster than linear. Not a lot, but a little bit faster. And so what we're going to do is we're going to fit a cubic polynomial to this. Okay? And so if you think about what a cubic polynomial is it's actually a linear polynomial which has a constant term, an x term, an x squared term, and an x cubed term. Okay? So it's the polynomial is going to look like y equals a0 plus a1 times x plus a2 times x squared plus a3 times x cubed. Okay? And so we want to know what that a0, a1, a2, and a3 are. Really, that's what we're interested in. Okay? And so if I wanted to fit a cubic polynomial to this, I can actually just go through. I already know what x is. I can figure out what x squared and x cubed are pretty easily. So this is a2 squared. This is a2 cubed, which for one are both 1, but for the other ones get more interesting. Okay, so I've got x, x squared, and x cubed. And I'm actually going to, for reasons that have to do completely with Excel and nothing to do with mathematics, I'm actually going to move the x term over here as well. Just another copy of it. And that's just going to make it easier to deal with Excel when we do the regression. Okay, so what we're going to do now is we're going to do a multiple regression. So this is just like the regression we did before. The ideas are all the same, except it gives us multiple variables. So it's going to give us, rather than just an mx plus b like we had before, it's going to give us a0, a1, a2, and a3, where each of those coefficients are multiplied times these particular numbers. Okay, so this is located under the data tab. So remember, I had you install the data analysis tool pack. If you didn't do that, this won't show up. But if you go to data, you can go to data analysis, find regression, and set this up. So we input the y range, so the y values for our data. Notice I caught the top one. That's important to catch the label. The x range, I'm going to select all of these values, and that's why I moved the x over to be next to them, was just to make it easier to catch all of these. Otherwise, Excel gets confused. I'm going to select labels because there are labels here inside the data, and that's going to show up in our regression coefficients. And then I'm going to hit output range and select a cell down here. That's just telling it where to put the data. Okay, so once I do that, I get this summary output table, which is pretty intense. You can see here there's a bunch of statistics. So one of them is the r squared value, so 0.972. That's saying that we're catching 97.2% of the variation in our regression. That's pretty good. There's actually the adjusted r squared, for those of you who've done any statistics know is actually a little bit better, but you can see they're not that different here. Okay, so again, just like we did before, an r squared close to 1 means that our regression is pretty good. The main thing that we're interested in down here are the coefficients. So you can see they're labeled intercept, x, x squared, x cubed. So those are the coefficients we want to use to predict our values, our y hat values. So if we want to do a y hat, I'm going to do that here. So these are what the regression model predicts for a particular x. Okay? And so I'm going to put this in. So starting with C37, C38 is our intercept. That's our A0, plus C39 is our A1, so that gets multiplied by x plus C40 times x squared plus C41 times x A2 cubed. Okay? And so you can see that predicts a value y hat of 7.46 when the actual value is 6.13. But you can see as this goes along, this actually is predicting y hat values that are pretty decent. So if you go ahead and graph this, so I'm going to select my x and y, my original, my y hat. I'm going to graph these as a scatter plot with lines. You can see that your blue data, that's your original data, and then this is the cubic polynomial that we fit to it. It's a really nice fit. Now I set this data up specifically to be cubic. I found it using a cubic polynomial and then some random variation. So I expected it to fit pretty well, but you can see this gets you a really nice cubic fit. It explains most of the variation. Okay? To do the same thing with the Fourier polynomial, which is in the second tab here, is exactly the same idea. Everything's just more complicated. Okay? So you can see here, I've got my x and my y values. If you look at them in the graph, you can see there's very naturally this periodic pattern. And the first thing I need to do is see how frequently it repeats. Okay? And so what you can see is if you're starting at 1, you're coming back across a similar kind of place at about 9. Okay? So you've got a period of 8. And you can see it repeats once from 1 to 9, once from 9 to 17. So this is a period 8. And that's the first thing you need to figure out because that's going to go into your individual terms for the Fourier polynomial. So that's going to determine that k, how often you want to repeat, that's in your denominator. Okay? So I'm going to take sine of 2 pi x over 8, cosine of 2 pi x over 8, sine of 4 pi x over 8, cosine of 4 pi x over 8. So just 4 terms. You could keep going, right? You could do sine of 6 pi x over 8, cosine of 6 pi x over 8 if you wanted to, and keep repeating. But this is enough for this one. Okay? So what you can see then is I just put those in. So to do sine of 2 pi x over 8, that's sine of 2 times pi. Remember to put these parentheses after pi. Pi is a function in Excel that gives you the value of pi, times a2, which is our x value over 8. Similarly, cosine of 2 pi x over 8, sine of 4 pi x over 8, cosine of 4 pi x over 8. Okay? And so once I had those, I went through and did a regression the same way. So I went to data, data analysis, selected regression, highlighted my y values for the output, highlighted all of these x values for the explanatory variable, for the independent variable. Okay, so all 4 of these, and so I got coefficients for all of them. I got an intercept. You're always going to get an intercept. And then I got sine 2 pi x over 8, cosine 2 pi x over 8, for sine 4 pi x over 8, cosine 4 pi over x. These are the coefficients of those terms. And then when I did my y hat, just like we did before, I took the intercept plus the sine of 2 pi x over 8 term coefficient times sine of 2 pi x over 8 plus the next coefficient times cosine of 2 pi x over 8, next coefficient times sine of 4 pi x over 8, next coefficient times cosine of 4 pi x over 8. Okay? And so when I did that, I got my y hat predicted values. And you could see when I graph these, y versus y hat, I get this really nice trigonometric function that follows my data pretty closely. Again, exactly? No. It's never going to be exact, though it can get exact pretty quickly. If you added a few more terms on, it would actually be exact. So I shouldn't say that. But we want something that generally follows it, but maybe doesn't echo it completely. And you can see the r squared here is 92%, which isn't bad. Okay? So that's how you fit these intrinsically linear models in Excel.